Well, hello everyone, and welcome to FPGA Design with Verilog. This is the third lecture in this video series, and today we're going to talk about behavioral modeling. So in this lecture we're going to talk about sequential logic, including latches and flip-flops, finite state machines, or FSM for short, counters, and register transfer level, or RTL modeling. So sequential logic overview. Sequential storage devices store state. Their output depends on current inputs and previous output or state. They are modeled using procedural blocks or always blocks and are triggered by edges or signal levels. So latches are level sensitive and flip-flops are edge triggered. So a D latch. When enable is 1, the output Q follows the input D, so it's transparent. When enable is 0, output is Q and it holds its previous value. It is level sensitive, depends on the logic level of the enable signal. So here we could declare a module called D latch with an output of type register Q, an input wire D, and an input wire enable. So always at whenever either enable or D changes begin. If we are enabled, Q is equal to D. So transport if enabled, and else Q holds the previous value. Note, sensitivity list includes enable and D. No edge clock is used. Synthesizes into a latch, not a flip-flop, and latches are usually avoided in synchronous design because they complicate timing. A D flip-flop edge triggered. On each positive clock edge, input D is sampled and stored in Q. Between edges, Q remains constant. So we declare a module called D_FF with an output Q, input clock, and an input wire D. So always at the positive edge clock, we set Q equal to D. It is triggered by a positive clock. It is used as a non-blocking assignment required for sequential logic, and this will synthesize into a D flip-flop. So here's a D flip-flop with an asynchronous reset. On reset signal, the output immediately goes to 0 regardless of the clock. Otherwise, it acts as a normal D flip-flop. So we declare a module called DFF async reset, where we declare an output Q, an input clock, an input reset, and an input D. So always at positive edge clock, or the positive edge of reset. If we reset, Q is set equal to 0. Else Q is set equal to D. Note, sensitivity list includes the positive edge reset for an asynchronous response, and reset overrides clock behavior. This is the most common flip-flop used in FPGA and ASIC design. A D flip-flop with asynchronous reset and preset. So a reset forces output to 0, and a preset or a set forces output to 1. Both are asynchronous. There is an immediate effect independent of the clock priority. If both are asserted, the reset signal usually takes precedence. So we declare a module called the DFFF async reset preset. We declare our variables, and either at the change of the clock, the reset or set. If reset, we set the Q equal to 0. Else, if set, we set Q equal to 1, and else we set Q equal to D. Both asynchronous controls listed in sensitivity list, and control logic order defines priority. D flip-flop with synchronous enable behavior. Samples input only when enable is 1. Otherwise, Q retains previous value. Reset is still optional, can be synchronous or asynchronous. So in our module, we do at the change of the clock or reset. If we reset, we set Q equal to 0. Else, if we are enabled, set Q equal to D. Notes, input is evaluated synchronously inside a clocked always block. Output updates only on clock edges when enable is equal to 1. So in summary, you can see that in a latch, we are level sensitive. There's no resets. There is an enable, and this is our sensitivity list. So it's transparent when enabled. A D flip-flop is edge sensitive. There's no reset. There's no enable, and this is our basic Verilog sensitivity. So we're a basic storage element with an asynchronous reset. This is where what we declare in the sensitivity list, a clock or a positive edge reset, and we reset immediately. With a flip-flop with an asynchronous reset or preset, this is our Verilog sensitivity list. We declare a clock, a reset, or set, and is independent of reset/preset. And then a D flip-flop with synchronicity enabled. This is our Verilog sensitivity list. So you can see it's similar to asynchronous reset, and it updates only when enabled. So next, finite state machines. A finite state machine is a sequential circuit that has a finite number of states. It transitions between these states based on inputs and generates outputs based on the current state and sometimes inputs. An FSM consists of 3 parts. A state memory block stores the current state. The next state logic determines what the next state will be. And output logic determines outputs based on the current and possibly next state. So there's 2 types, more and mealy. More depends, the output depends on the current state only, and the mealy output depends on the current state and inputs. So think of sequence detectors or traffic lights, and then we have serial data decoders as an example of a mealy machine. So design steps. There's define the states, define the state transitions, define outputs, and write the Verilog code with separate blocks for state memory, next state logic, and output logic. So in Verilog, an FSM typically uses 3 always blocks, as you can see here. An example, a 3-state more FSM. Let's design a simple FSM that waits for an input in, goes through states idle, wait, and done, and asserts output done when in the done state. So define the state encoding. So we declare a module called FSM example with a done output, clock input, a reset input, and an input. So first we declare our states. So we declare a 2-bit parameter, and idle is set to 0, wait is 1, and done is 2. Next we declare 2-bit registers called state and next state. So next we define the state memory block. This stores the current state. So always at the change of a positive edge clock or a reset. If we reset, the state goes into idle, else the state goes to next state. Alright, this is the next state logic block. So always at any change, if we declare a case. So for any state, if we're in the idle, we begin. So if we input, the next state goes to wait. Otherwise, we stay in the idle state. If we're in the wait state, the next state goes to done. And then if we're in the done state, if there is no input, the next state goes into idle, else the next state stays at done. And then the default is the next state is in idle. Finally, our output logic. So always at any change, if for any state, if we're in the idle state, we output 0. If we're in the wait state, done is 0, and if we're in the done state, done is 1, else done is 0. So in the summary, these are our states, and this table shows you what changes as we go through the state machine. A mealy finite state machine example, where the output depends on the input. So we declare a module called FSM mealy with an output, a clock input, a reset, and an in. We declare a parameter where we set the S2-bit parameter, where we set the 0 state to 0, and the S1 state into set equal to 1. We declare a 2-bit register called state and next state. So our state memory, always at the positive edge clock or the reset state, or the reset. If reset, state is S0, else state is set equal to the next state. The next state and output logic. So always at any change, if we're in state 0, we begin, out set equal to 0. If in, so it's 1, next state is S1, else the next state is S0. And if we're in the S1 state, as we set out equal to in. If 0, the next state is equal to state 0, else the next state is equal to S1, and in the default the next state should be just S0. So, in summary, Use non-blocking statements in the state memory block. Use blocking assignments in combinational blocks, and always include a default state in the case statement. Use parameters or local parameters for name states. For simulation, include display statements or dump files to trace state transitions. So we have our state variables, state memory block, next state logic block, output logic block, and a mealy FSM. So our state variables to store current and next state, our memory block to update the current state and clock edge, our next state logic to determine the next state from the inputs and current state. Our output logic block determines the outputs from the current state and sometimes input 2. And remember, for a more, the output only depends on the current state, and for mealy, the output depends on the state and input. Counters. A counter is a sequential circuit that increments or decrements its stored value on each clock cycle. Counters are used for frequency division, event counting, time delays, and state sequencing. They are implemented using flip-flops and combinational logic, but in Verilog we model them at a higher level using procedural blocks. A counter typically includes a register, a clock input, and an optional reset, enable, load, or direction. All updates happen in an edge-triggered always block. A basic counter is the simplest type. It counts up on every clock cycle and resets to 0 on reset. So here in our module counter basic, we have an output count, an input clock, and an input reset. So always at the positive edge of the clock or reset. If we reset to 0. Otherwise, a count gets incremented by 1 on each clock cycle. If we want to introduce range checking, so sometimes you want a counter to wrap around to 0 or any other value instead of overflowing. So we declare a module called counter range, and always at the change of the clock or reset, if reset 0, else if count is equal to 9, we set count equal to 0 to wrap around, else we increment the count. Now the enable signal. So this counter only increments when enable is 1. So as you can see here, we only increment count when enable is true. A loadable counter can preload a value when load is 1. So we input our load. So at the change of the clock or reset, if reset 0, so if we have a load, we load in the new value into count, and then we increment. An up-down counter can increment or decrement based on a control signal. So we declare our control signal, and then at every clock change, as the control signal is if up is true, then we count up, otherwise we count down. So, and then finally, up-down counter with range limits and enable. So we combine the features that we previously learned. So if we reset, it's 0, else if enable is true. If up, we count up, but if count is 9, then we reset to 0 first, and then and else if count is 0, we reset to 9, and then we decrement the counter. And then finally, register transfer level modeling. A register transfer modeling describes a digital system in terms of data storage elements, data transfer operations, and combinational logic that processes or routes data between registers. It's called register transfer level because it focuses on how data moves between registers and each clock cycle. So for a register are flip-flops that store data on a clock edge. A combinational logic processes data between registers. A mux selects data between data sources. A bus is a shared data path. And a shift register will sequentially shift bits. So modeling a simple register. So we declare a module called a register basic. So at the change of every clock, if reset, we clear the register. Else we set Q equal to D. We load input data into the register. Register with enable. Similar to last time, except if we're enabled, if enable is true, we set Q equal to D. Registers as agents on a data bus. In larger digital systems, many registers share a common bus. Only one device drives the bus at a time. This mimics real microprocessor architectures, where multiple registers transfer data across a shared internal bus. Example, two registers sharing a common 8-bit bus. So we declare a module called bus example with an output wire, an 8-bit output wire called data out, a clock, a reset, a selection wire, an input wire, and a data input wire. We declare a 8-bit registers called AB, an 8-bit wire called bus. So at register A, at the change of any clock, cycle, or reset, if reset A equal to 0, else if load A is true, then A is set equal to data in, and similarly if load B is true, then B is set equal to data in. And here we have some tri-state bus driving. This is not synthesizable. So we assign bus equal to if selection A is true, then A, else high impedance, else, or then if selection B, if that's true, then we select, and then we set assign bus equal to B, else we get high impedance, and the output from the bus, data out will be equal to bus. Alright, RTL example with MUX bus synthesizable version. So since many modern FPGAs don't support tri-state buses, you need to model the bus as a multiplexer. So the only difference is data out will be set to if selection A is true, then data out will be equal to A, else data out will be equal to B. Modeling shift registers. So here's an example of a right shift register. So we're going to shift the bits to the right. So we set data out equal to the in bit and the data out, and then the data outs for the 7 bits of data out. New bit enters the most significant bit, and old bit shift to the right. Similarly, for load shift register, the new bit enters the least significant bit, and the old bit shift left. A bidirectional up-down shift register. So we set data out equal to the in bit and the data out, else data out is equal to data out, comma, in bit for the left shift. And parallel load shift register. To do a parallel load, we say if load is true, data out will be equal to data in, else we shift left. Alright, so that concludes the end of this lecture. Thank you very much for watching.